this seminar today. I'm very happy to introduce Baptiste Rognerud, and who is going to talk about examples of combinatorial objects and quiver representation theory. So he's at Université Paris Diderot, and I'm at the University of Leeds that I'm hosting today. So there are two more things I'd like to say. First of all, you see in the chat, there is a Zulip link which works. So if you want to ask questions which will stay there after the seminar, you should put them in the Zulip link. And there is also a link to the slides of Baptiste, now again at the bottom of the chat, where you can see the slides. So during the talk, you can put messages in the chat, and I'll try to monitor that so that Baptiste doesn't have to do it.
Thank you.
Okay, well then you can start.
Yes, thank you. So first of all, I would like to thank the organizer, and in particular Dominique and Kurush, for the invitation. Then I will try to share my screen. Okay, so let's see if it is working. Yes. So today I will speak about quiver representation, and more precisely, I will focus on some combinatorial aspect of quiver representation theory. So I chose this topic even if it's not very new, because maybe you don't really care about quiver representation theory, but hopefully you will like the kind of combinatorics that I will present you at the end. And yeah, maybe you can even help me a little bit, because I think this combinatorics is new, but I'm not completely sure, and I am always looking for new information about it. Okay, so let me start with a little bit of introduction on quiver representation theory. So I will fix, so let Q, I don't know why this is smaller than I was expecting. Okay, let me just change the size of my, well, okay, no, I cannot do it. Okay, no problem. So let Q be a quiver. Oh, can you see it? I don't know, for some reason I have a very large lag. Do you hear me?
Yes.
We hear you fine, but if you don't see anything after the S comma.
Okay.
Now we do.
Yes, okay. So there seems to be like 1 second lag between the tablet and the computer. Okay, no problem. So let Q be a quiver, and a quiver is just a fancy name that we use in representation representation theory for finite directed graph. Okay, so I'm checking if it's working. It's very slow for some reason. Okay, so just a finite directed graph. So I will show example in a couple of minutes to explain exactly what I mean by finite directed graph. But maybe just I want to give a motivation on why we should look at representation theory of such object. And this is a theorem of Gabriel, probably a less known theorem of Gabriel from the 70s, where he proved that if you take a finite dimensional algebra, so if A is a finite dimensional algebra over some field K, then the category of module over this algebra is equivalent to the category of representation of some quiver over the field K modulo some relation, where Q is a quiver or is a quiver, and this I is some kind of set of relation. So in some sense, if you can understand all representation of quivers modulo relation, then you can understand all the representation of the finite dimensional algebras. So this is really maybe the first motivation. The second motivation is that representation of quiver is kind of fun. So I will try to explain this today. Okay, so let me move to some example of quiver that I already prepared. So the first one is the equioriented AN quiver. So just some kind of a line with all the arrow going in the same direction. The second quiver is something called the Jordan quiver. So you see that in my directed graph, I allow the loops. Then I have the Kronecker quiver on the generalized Kronecker quiver. And you see that I allow multiple arrows between the vertices. And then you can imagine that you can construct some weird and difficult quivers like the example that I gave here. Okay. So what is a representation of a finite quiver? Well, this is also not very difficult. So you choose, for that, you choose a field. Oops, this is not the good pencil. So you choose a field, and then a representation of a quiver Q is just the data of vector space attached to each vertex of your quiver. And in this talk, I will mostly do finite dimensional representation. So I will consider finite dimensional vector spaces. And then you also want a linear map, a linear map between two vector spaces every time that you have an arrow in the quiver. And this is it. You don't ask any more information about it. And then you want a category of representation. You want a way to compare two different representations of the same quiver. So this is done by looking at morphism of representation. And the morphism between two representations is just a collection of linear maps between the vector spaces attached to each of the vertex, to each vertex of the quiver. And you want some kind of functorial property. So for each arrow in the quiver, you have two ways to go from the vector space associated to the vertex I in the first representation and the vector space associated to the vertex J in the second representation. First by moving in the quiver and then applying the morphism, or apply first the morphism and move in the quiver. And of course, these two ways should give the same answer, the same result. Okay, so this is a representation, this is a morphism, and of course, an isomorphism is a collection of isomorphism of vector spaces, or a collection of bijective linear maps. Okay, so let's do examples even. So in the first case, maybe the easiest possible case of the quiver of type A, representation is just the data of one vector space associated to the first vertex, a second vector space associated to the second vertex, and a linear map between these two vector spaces. And if you want to classify the vector space, the representation up to isomorphism of representation, maybe you can first choose a basis for V1 and V2, and you end up with the data of a rectangular matrix A between two vector spaces Kn and Km. And if you want to compare with another one, of course, they must have the same dimension. So you have another matrix, rectangular matrix B, and an isomorphism between these two representations is just the data of an invertible matrix P in GLN of K and an invertible matrix Q in GLM of K. And saying that this is a representation means that this square commutes, and this means that A is equal to Q minus 1 BP. So in some sense, classify the representation for this quiver up to isomorphism is this equivalent to classify the matrices up to this kind of multiplication. So we want, oh, I really have difficulty with the tablet to classify matrices up to, I think in French it's called matrix equivalence. I'm not sure in English, but you see what I mean. Matrix equivalence. And this is something like that we learn in, I don't know, first year of university. There is a normal form for this equivalence, which is given by this kind of matrix. You just perform the Gaussian elimination algorithm, and you end up with a matrix having an identity on the diagonal and 0 everywhere else. And then you see that this is classified by 3 integers, classified by, you need 3 parameters. The first one is the dimension of the first vector space. The second is the dimension of the second vector space. And the last is the rank of the endomorphism, the homomorphism of the matrix. Okay, and you see that this is 3 discrete parameters. So this is the classification for the first example. Maybe we move to the Jordan quiver. So in this case, you have only one vector space. So a representation is just the data of one vector space with an endomorphism of this vector space. And if you want to classify this representation up to isomorphism, you choose a basis as before. So you end up with a matrix. This time a rectangular matrix, and you want to compare two rectangular matrices, and an isomorphism is just given by an invertible rectangular matrix P, and you want this to commute, so it means that A is P minus 1. Ooh. A is P minus 1, B, P. Okay, and so you want to classify the rectangular matrices, square matrices, sorry, square matrices up to this notion of similarity. And let's say you worked over a field of complex number. This is done by the canonical Jordan form. canonical Jordan form. And so you have this Jordan block Gn of lambda with lambda on the diagonal and 1 above the diagonal and 0 everywhere else. And then you see that the classification here involves two parameters. So you have two parameters. The first one is the size of the block which is a discrete parameter. And then you have the eigenvalue, lambda, which is not a discrete parameter. Okay, so in this case, it's still quite easy to classify the representation. So maybe we move to another quiver, so the two loops quiver. And if you play the same game, you see that a representation is just one vector space with two linear maps, two linear endomorphism, and then basically you end up to try to classify the pair of matrices let's say A and B, but up to simultaneous conjugacy. Simultaneous conjugacy. And it turns out that this is more difficult. And in fact, this is, I think it's unknown. So it's a linear algebra problem, which we cannot solve. Okay. So as you can see, basically, if you stay with the definition, representation theory of quiver is basically linear algebra. Maybe very difficult linear algebra, but linear algebra. So because it's not so easy to do a lot of things with linear algebra, it's maybe better to try to simplify more the problem. So I will introduce the notion of indecomposable representation. And it's not difficult. A representation is indecomposable if it's not the sum of two non-zero proper sub-representation. So it's like the prime number for representation. And like the theorem of, I don't know the name, the fundamental theorem of arithmetic, we have the same for representation theory, which is called the Krull-Riemann-Schmidt theorem. And it says that any finite dimensional representation of a quiver, of a given quiver, is isomorphic to a direct sum of indecomposable representation. And the important part is that this decomposition is unique up to reordering the components. So if you want to understand all the representation theory, it's basically enough to understand, it is enough to understand the indecomposable one. Okay, so let's do it in our example. So we come back here. In the first case, this is a very easy example. There are only 3 indecomposable. So you have, let's say, A, which is you plug the field for the vertex 1, and you put 0 for the other vertex, and you put the 0 map between them. Then you have B, which is the other one. So you plug the field in the vertex 2, And then you have C, which is of dimension 2, where you plug the field everywhere and you put the identity map between the two fields. And it turns out that if you have a representation like V, then V is isomorphic to A times, so the first indecomposable will appear number of time equal to the dimension of V1 minus R, plus B will appear to the dimension of V2 minus R, plus C will appear R times, where R is the rank of the linear map alpha, and of course Vi is the dimension of Vi. So this is the most simple example of quiver. This is something called a finite representation type quiver. Finite representation type. So we can compute everything. Is the from an indecomposable a coproduct of indecomposable? Yes, at least if you work with finite dimensional, yes. If I understand correctly. Okay, so let's move to the Jordan quiver. So the Jordan quiver, the indecomposable are just written here. They are the Jordan blocks. And in this case, you see that you have infinitely many indecomposable because you can find Jordan blocks of size as large as you want, but you see that if you fix the dimension of the indecomposable module, then you have only one parameter family. So it's infinite, but it's still manageable. So we say that this is tame representation type. And then we move to the last example of the loop quiver. So in this case, the classification of representation is unknown, but if you move to indecomposable, it's still unknown. And this is an example of a wild quiver, of wild representation type. So in particular, you can find a family of representation with two parameters. So for example, this one. This is a two-parameter family. Oh, I can't write it. And in fact, it's in some sense, it's impossible to classify the indecomposable representation over such a quiver, because if you could, you would be able to classify the representation, the indecomposable representation of over any quiver. So in particular, you can imagine that you take the representation of the quiver with one vertex on 1 million loops, and you see that this is not really possible to write down the indecomposable. Okay, so these are the three main examples, and these three examples are basically all that exists. So we have a trichotomy like this, a trichotomy. So a quiver, and this is actually more general, is either of finite representation type, and we exactly know when this happened. This is a theorem of Gabriel, and in this case, it means that the underlying graph of the quiver is a dinking diagram. Maybe it is tame. And we also know when this happens. This is in the extended thinking case. And then you have the white quiver. And these are all the others. So in particular, it means that most of the quiver are wild. And in particular, it means that we cannot really understand the full representation theory of a given random quiver. So it's why we try to find easier question that we can solve. So in particular, it's a good question to try to find interesting families of representation. Or maybe subcategories. Subcategories. Okay, and before providing example, maybe I should say that there is some kind of combinatorial principle. Combinatorial principle. Oh, I really have difficulties with the tablet today. So in general, if it's interesting from an algebraic point of view, so if it's interesting for the representation theorist, when you apply the theory for the AN quiver, in the case of the AN quiver, it gives interesting combinatorics, or maybe famous combinatorics. It gives famous. Or sometimes it's not known, so or interesting. Interesting combinatorics. So it's not really a theorem or something. It's not based on mathematics, but it's more like based on experience. So let me show you a small list of what I have in mind. So let me check with the computer if we see the same. So here is just the beginning of a list that I made yesterday. So on the left, you have the algebraic object. Then you have the number of isomorphism classes of this object. Then I give maybe the simplest combinatorial interpretation of this object. And if there is natural structure of poset on this object, I also give what it is. So we will not look at all the examples, but maybe we should start with the simple example. So what are the simple module, the simple representation? They are in bijection with the vertices of the quiver. So of course, in the case, or maybe I should say what is the AN quiver, in case we forgot. So this is just this equioriented quiver of type A. So you have, of course, n simple representations, and maybe the most useful combinatorial interpretation is the fact that this quiver is an orientation of a thinking diagram. So you have a root system attached to the thinking diagram, and the simple representation correspond to the simple roots of this root system, and the indecomposable representation, they correspond to positive roots But you can see that you have many other combinatorial objects that have interpretation in terms of representation theory. So maybe I like this one, the complete exceptional collections that I will not define. But anyway, you see that you have a fused Catalan number of them. More precisely, you have the number of ternary trees. So this is the number of ternary trees. And it's also the number of something called non-crossing trees, or which is probably the most useful combinatorial interpretation for these objects. Then I like Catalan numbers. So here is a bunch of Catalan numbers in representation theory. You have the so-called tilting module, which correspond to the binary trees. And then there is a natural partial order on these tilting modules, and this gives you the Tamari lattice. Then if you want to count some special subcategories, you also find the Catalan numbers, but shift by one for the torsion classes. And this also gives the Tamari lattice. And maybe if you like non-crossing partition, they also have an interpretation in terms of some special categories. And well, you see that the Schroeder numbers, they are also quite easy to interpret in this setting, and many, many more. So today, what I want to explain is these 2 points. Oh, yes. So I want to explain what are the so-called faithfully balanced module for the quiver of type AN. And we will see that these correspond naturally to something called increasing binary trees. So they are counted by n factorial, and they correspond to increasing binary trees. Okay, so this is just a list of examples. And maybe if you found in your research interesting combinatorics in type A, you want to try to generalize to a more general family of algebra or quiver. And the quiver of type A is very nice because it is at the intersection of many different things. First of all, it is an orientation of a linking diagram. It's also the Hasse diagram of total order. So maybe you can try to generalize your result to functor over posets. It's also something called a gentle algebra or a Nakayama algebra. So you can also maybe try to generalize. And most of the time, looking at your combinatorics, it should be clear what is the easiest generalization. If your combinatorics involve a root system, well, probably you should look at other linking diagram. If it's involves Young diagram, maybe it's better to look at something called Nakayama algebras. Okay, so do you have question before that I move to the second part of the talk? No, it's okay. So I will move to faithfully balanced module. Faithfully balanced module and their classification for this quiver of type A. So I should say that this is a joint work with Bill Crowley-Bovey. Biaoma and Julia Zauter. And they are all, well, Biao is not anymore, but they are part of the University of Bielefeld. Okay, so let me give the definition of a faithfully balanced module. So a module M over a ring or finite dimensional K algebra, a ring A is faithfully balanced, so I will just write FB if the natural map going from A to the endomorphism ring of the module M viewed as a module over its endomorphism ring. And this map is just, you send an element A to the multiplication by A. So let's say I take left module. And you ask that this map is an isomorphism. Okay, so let me just give a remark. First of all, this notion is not new. And actually, it's the opposite of new. It's very old. They appear in the so-called Schur-Weil duality. Schur-Weil duality. And they also appear in Thrall generalization of self-injective ring. Generalization of self-injective ring. And this is, I think it's 48. So yeah, not very new. But for some reason, it seems that no one really tried to classify them before our work. So no classification. No classification. So maybe I should give theoretical examples before giving more explicit examples. So the first example of faithfully balanced module are the so-called generators of the category of module, generators. And in particular, the progenerators, they are example of faithfully balanced module. And these are useful because they produce Morita equivalencies. So they produce equivalencies of categories. But you also have something slightly more general. You have the, well, not more general, in some sense it's perpendicular. You have the tilting modules, and this, they give example of equivalence of derived category. Derived categories. So they are even more useful than the first one. And in particular, these two facts, this means that the family is huge. So it is a huge family. And if your algebra is infinite representation type, then you will have infinitely many faithfully balanced modules. But still, let's look at the example of the quiver AN, and you will see that the combinatorics is quite nice. So in the case of the quiver AN, which I recall is just this quiver, then let's see the classification. So first of all, I need to define a bunch of modules for this quiver. So every time that you have an interval in the total order 1 to n, you can construct a module, a representation of this quiver just by doing the easiest possible thing. So you plug the field k at the vertices in the interval. Oops. Okay, so this is I, this is j, and this is I plus 1. And of course, you want a representation, so you need maps. So you put the 0 maps and the identity maps between the fields. So this gives you a representation, which is called interval representation. And the claim or the fact is that they are all the indecomposable representation for this quiver. They are all the indecomposable for the quiver AN. So using the Krull-Rimac-Schmidt theorem, if you take any representation, finite dimensional representation, is a representation of AN, then this you can write as a direct sum of this interval representation. And they will appear with some multiplicity, which I write Nij. And because of the unicity in this Krull-Rimac-Schmidt theorem, we know that M is characterized up to isomorphism by this sequence of integers, by the sequence Nij. Okay, and in particular, we will give the name of basic to M if each indecomposable appear at most once. If Nij is in 0, 1 for every ij. Okay, and I will mostly focus on basic module from now on. So the nice thing with basic module is that we can detect them using this combinatorial model. So I consider a Young diagram of staircase shape like this, and to each box, each box represents the interval module. So the box ij represents the interval module mij. And there is a bijection. There is a bijection between the isomorphism classes of basic module and the fillings of this diagram of Tn by some black dot. So you put a black dot in a box if the corresponding interval module is a direct summand of your basic module. So you can really detect all the indecomposable, all the basic module, sorry, just by looking at this kind of fillings. And if you want to understand the category of representation, then you need the morphism. So these are not present in my picture, but in fact, the morphism, they go like this. You have vertical morphism and you have horizontal morphism. So in fancy terms, this is the so-called Auslander-Ryden quiver of the representation of the category of representation of this AN quiver. Okay, so this is a very useful gadget, combinatorial gadget. So maybe let me give an example. An example of what we can do with it. So maybe first, what are the simple modules? So the simple module, they are the last box of each row. The projective module, they are in the first column. The injective module, they are in the first row. And then what is a tilting module? So a tilting module if you use this gadget, is a filling with two properties. First, it is of size n. And the size of a filling is the number of black dots, so of size n. So of course, this is a tilting module for this quiver AN. And for any two intervals in this filling, and any two intervals are either contained in each other or disjoint by at least one integer. Integer. And yeah, maybe it's an exercise to check that there are Catalan of them.
Sorry, what do you mean by disjoint by at least one integer?
Well, I mean that ij, and so I mean that the next one should be j plus 2.
Ah.
Yes, so you should have a gap of at least one integer between two such intervals. And it turns out that there are Catalan of them. And I think the first one to realize that is Gabriel in the 80s. So it's really not difficult, but yeah. Okay, so yeah, these are the tilting module. And maybe I should say what is a phase fully balanced module. So I give the theorem and then I explain the combinatorics. So this is, let's say, the first result in our article. So a phase fully balanced module is a filling satisfying three conditions. Satisfying. The first one is very easy. Let's see if it's no. Okay, so the box with coordinates 1n should contain a black square, a black circle. And this is some kind of root property. I will explain this in a minute. The second condition is a local condition. So if the box ij contains a black circle, then its cohook is non-empty, and I will define the cohook in a moment. And the last property is a very similar property, but for something called virtual boxes. And so the virtual cohook are also non-empty. Okay, so I will go back to my picture and explain what are the virtual boxes and the cohook. You will see that it is not so technical. So the virtual boxes, you just add one box at the end of each row. So in some sense, you remember that they come, this diagram Tn, they come in a family indexed by n, and you see Tn inside Tn plus 1 in some sense. And what is a cohook? Well, maybe I draw a virtual cohook here. It's the set of boxes above and on the left of a given box. So this is the virtual cohook of the red square. This one. And maybe I don't draw it, but I think you understand. For the non-virtual boxes, it's the same rule. All the boxes above and on the left. And so a faithfully balanced module with this gadget is a feeling such that you always have a black circle on the top left of your diagram. All the virtual cohook should be non-empty. And let's say that you have, I don't know, you have here a black circle, then you look at the virtual cohook, no, not the virtual, just the cohook of this. And this should be non-empty. So maybe you find something here, and then you start again with the cohook of this guy, and this should be also non-empty. So you must have somewhere, no, it's not the good color. You must have somewhere black circle. So basically it means that you can always find a path made of horizontal and vertical edges from any point to this top left square. So this is why I call it a root. You know, this is like a tree property in some sense. Okay, so this is the combinatorics for faithfully balanced module. And when you have this theorem, now you can start to play with it, and maybe you can count the number of faithfully balanced module. And the first result is that the number of faithfully balanced module for this algebra is something called the Q analog of n factorial at Q equal 2. So this is product from I going from 1 to n of of 2 to the I minus 1. And if I remember correctly, this sequence starts with 1, 1, 3, 21, 315, and then 9,000 something. And so it's really, as I said, it's a huge family. It grows really fast. So this is the first counting result that we have. Then there is a curiosity. There is something a little bit strange. Using this result, we can see that phase-fully balanced module it has size at least n. And n is the number of simple module. So it has size at least the number of simple module. And we have algebraic interpretation for tilting module and generators, but we don't have algebraic interpretation for phase-fully balanced module. And in particular, there are algebras with where there exists phase-fully balanced module with size less than the number of simple. So this we don't really understand what it is. And let's say that we call by FBN the set of phase-fully balanced module of minimal size. Then we can count them and we find that there are n factorial of them.
Sorry, so by size you mean length?
I mean the number of indecomposable summands. So the number of black circle.
Oh, okay. So in the Crude-Schmidt decomposition. Okay.
Yes, yes, exactly.
Okay, thanks.
The number of indecomposable summands in the Crude-Schmidt decomposition. Yes. Okay, so yeah, I forgot to give the list, but okay, this is the list for A3. So you can see that to construct a phase-fully balanced from the list, so you take one diagram, for example, this one, and the black square, they must contain a black circle. The white square, they must be empty, and the squares with a cross, you can put or not a black circle in it. And if you are quick with counting, you see that there are indeed 21 of them, and you see that there are 6 of them with only 3 of size 3. And these are the tilting, are the 5 tilting, and this is a phase-fully balanced of minimal size, which is not a tilting. Okay, so I will finish here, but let me just comment a little bit on this corollary. The third point here, we have a bijective proof of that. And as I said before, we can prove that the phase-fully balanced module of minimal size, they are in bijection with the so-called increasing binary trees. Maybe let's just draw how the bijection works. Okay, so let's say that we take the tilting. Then you can construct, when you have a tilting, you can construct a binary tree in a very simple way. You put the virtual boxes, and then you put edges between the vertices and edges between the vertices and the virtual boxes. And then this gives you a binary tree. So the idea of the bijection is to do the same with the phase-fully balanced module. But if you do that, you have a small problem. If you look at this example, so you do the same rule, and you end up with this tree. like this. And of course, as an abstract graph, these two are equal and the two modules are not. So in some sense, what we do is we consider something that we call interleaved trees, where you fix the position of the leaf and you don't allow to remove such kind of crossing. So in some sense, they are binary trees together with a shuffle of the leaves. And then you see that you can remove the crossing informally. If you push down this vertex, you can remove the crossing and you end up with a bijection with something called binary trees with level. Or if you prefer, you can keep track of the crossing with a labeling and you end up with something called increasing binary tree. And maybe I show the last picture. So there is also a very natural way to construct a partial order on faithfully balanced module of size n. And this gives you a lattice on n factorial, which seems to be new. And this lattice is not the weak Breuer order. So here are the example. But so for n equals 3, you see that if you forget the orientation of the quiver, you find the hexagon. And for n equal 4, you almost find the permutahedron, but in fact there are two additional edges, which are two dissection here. So it's it's really difficult to be sure that this is not a known lattice on n factorial. And well, if you know it, I will be very happy to learn about it. So thank you for your attention. Maybe I should stop sharing my screen and come back here. Okay.
Thank you very much for this very interesting talk. Are there any questions?
So sorry, can you repeat when you got Catalan numbers with those non-crossing arcs? What again was you count?
Maybe I share again my screen. Let's see. How can I do it? So is this in this list?
I think it's later.
Oh, later. Later, okay. Yes. So the tilting representation. So I count.
Yes.
I count the fillings of size n. So precisely n black circle. And when you have a circle in a box, you have an interval.
Oh, I see.
And two of them, they must be either disjoint by at least one integer or one containing the other. So if you prefer, this is just the binary trees. If you look at this picture.
Is it the binary trees? Why?
Yes. In this picture, if you draw the, so with my choice of notation for the diagram Tn, these are the binary trees.
Oh, I see. Nice.
Does the result extend to other linking quivers, ADE?
Yes, it's a very good question. So the combinatorics, so you have n factorial, which is the size of the Weil group. And this Q analog of n factorial, I think it's the number of points is the flag variety. So it's really, it looks like type A combinatorics, but we are not able to extend it. In fact, we can extend it to something called Nakayama algebras, where you still have this kind of Young diagram combinatorics.
Okay, thanks.
So in particular, the number depends on the orientation of the dinking diagram. This is probably the main problem for extending the result.
Okay.
Do you know any further properties of this lattice on n factorial many permutations?
So it should be something called semi-distributive. This is, I have not checked it, but according to Sage, it should be semi-distributive.
Is there any link with the Ptolemy diagrams or with the torsion classes?
Not so clear yet. It's we don't really know. So we obtain this poset is constructed by looking at inclusion of some categories, but they are not torsion classes or torsion-free classes. So to a faithfully balanced module, you look at the category of module generated by the faithfully balanced module. So this is like the fac of T. I don't know if you know the notation. And you can also look at the category of module co-generated by it. And the poset structure is given by inclusion of the fact category and reverse inclusion of the cogen category. But it's not clear what kind of category they are, at least to me.
And the virtual boxes, is there any interpretation, something like coefficients in cluster categories? Or?
I don't really know. It's an extension property, in fact. It's an extension between simple module property. But in terms of cluster, I don't really know.
I have a simple question. Is there somewhere where we can find 3 Catalan numbers?
Which number, sorry?
3 Catalan, or more general n Catalan, the number of fillings of rectangular tableaus, young tableaus, with n rows. Or 3 rows in this example.
Yes.
And Catalan gives the case too. Okay.
Yes.
And then maybe a bit more. So thank you for this very nice introduction to quiver representation. It was a new topic to me. Is there a theory when you replaced the target category, you had your vector space with linear maps in between by something else? For example, just sets with maps in between?
Well, you can certainly do it.
Yeah.
With sets, I'm not sure. I probably some people have looked at it, but at least you can take any abelian category. This makes sense.
What is their theory?
Sorry?
Sorry, is there a theory? Is there, yeah.
I'm not sure if there is some kind of well-established literature about it. But
okay.
you can also look to, so the target can be something called this kind of stable infinity categories, which come up in topology. And here there are some articles. So you have someone called Gustavo Jasso, and he has article on this.
Okay, thank you. Because the quiver reminds me of a dynamical system, right? So that's why I'm thinking of bijective map and
yes.
Yeah, okay, thanks.
Yeah, along very similar lines, I was wondering if you replaced K, your field, by the natural numbers and looked at semi-rings. So you still have plus and times, but you just don't have negatives. I think it's probably the exact same question, but do you happen to know anyone who's thought about that?
Yeah, I don't know, no. It's a very natural question, but yeah, I don't know if someone really wrote something about it.
And in your Gabriel theorem in the very beginning, you mentioned relations. Can you say anything about, are those relations on the category, on the quiver, or what were they relations on?
Yes, so maybe the easiest way of stating it is to consider the pass algebra of the quiver. So it's a quiver with basis all the paths in the quiver, and then you take an ideal in this algebra.
Mhm.
And maybe you ask some properties about this ideal. But...
So in particular, any category, could you subtract? If I had a commutative diagram, I wanted to add a commutative diagram to a quiver, could I subtract the two paths and make it equal to 0? And
yes, exactly. Yes. So for example, if you have a poset, then you look at the Hasse diagram of the poset. It's more natural to look at the quiver modulo the relation identifying any two paths that start and finish at the same points.
Right, yeah. Okay,
yes.
Nice.
Well, if there are no more questions, then let's thank the speaker again.
Thank you.
Thank you very much.